Hello everybody. Today we are here to discuss about multiplexers in digital electronics. So mainly in this presentation we would like to know what do you mean by multiplexer, a simple 2:1 multiplexer, 4:1 and 8:1 higher order of multiplexers, where these multiplexers are used, and realizing some logic functions using multiplexers. What actually is a multiplexer? In short, can be called as a MUX. It is a data selector or a digital switch which is going to connect to any one of the sources among multiple sources and then transmitted over a single line. So in a rough way, it can be called as many input, one output device. How does it look? How does a typical MUX look? As we can see, we have number of inputs, n number of inputs, and there are some special inputs called as select inputs. Depending on the status of these select inputs, the output is connected to any one of these inputs. These multiplexers come in the order of 2:1, 4:1, 8:1, 16:1, so on. Let us look at the simple 2:1 multiplexer. As we can see, two inputs, I1, I0. To select one among these two inputs, one select line would be sufficient. Whenever this select line is low, the output is directly connected to the I0 input. When select line is high, the output is connected to I1 input. Look at the truth table. So when S is 0, Z is just equal to I0. When S is 1, Z is I1. The logical expression to represent a 2:1 MUX would be Z is the output, I0, I1 are the data inputs, S is the select input. Higher order of a MUX, 4:1. As we can see, we have D0 to D3, 4 data inputs. To switch to any one of these data inputs, at least two select lines are required, A and B, and output Y. Symbolically, you can represent 4:1 MUX, the truth table corresponding to 4:1 MUX. So when the select lines both are low, D0 is the output. When it is 0-1 combination, D1 will be available on the output, or 1-0, D2, 1-1, D3. So next we would like to move waveforms of 4:1 MUX. The four data lines and the two select lines, the output Y. The sequence for the select lines is taken as during the first time T1 it is 0-0, then it is 0-1, then it is 1-0, then 1-1. The cycle repeats. When S0, S1 both are low, as we all know, D0 will be the output, so you can see a low state at the output. When the select status is 0-1, D1 is the output which is available in the second T state. Third 1-0 combination, D2, so low state is available on the output. 1-1, D3, which is again low, is available on the output. This continues. Next order of multiplexer, 8:1. The 8 input data, I0 to I7. To select one among these 8 inputs, minimum 3 select lines are required, S0, S1, S2. The combinational circuit corresponding to 8:1 MUX, which is also available in the form of integrated circuit, IC, with 151 number. The truth table corresponding to 8:1 mux can be seen here. There is an enable pin which is an active low pin. Means that whenever it is grounded or connected to 0 volt, only then the particular IC works or it gets activated. Selection of the multiplexer depends on the application basically, where you are using this multiplexer. Some of the MSIs 4:1 mux, 8:1 mux and even 16:1 mux are available. Look at the typical application for the usage of multiplexer. As we all can see, there are multiple sources, maybe a cable TV set-top box or a satellite, laptop sound card or a MP3 player station. All these are connected as the sources, as the inputs to the mux, and the output is connected to the sound system. This sound system is connected to any one of these sources, or you can see the data coming from any one of these sources will be available at this sound system depending on what is available on the pins A and B. So these are the select lines which are going to select one among these four sources. Look at some examples trying to implement a logic circuit using multiplexers, appropriate multiplexers. The truth table, as we all can see, you have three inputs, A0, A1, A2 and the output Y. Let us name these as 0, 1, 2, 3, 4, 5, 7 till 7. Look at the states, look at those patterns where the output is high. It is for 1, it is for 3, it is for 5 and 6. Simply using a mux, using a 8:1 mux, we can just do it by connecting 1, 3, 5, 6 to a high state and the remaining inputs of the mux grounded. This Y will be nothing but the min terms corresponding to the truth table. We have 4 min terms, which is in sort. On the similar way, if a Boolean expression is given and realized using a suitable mux, as we can see, there are only 3 variables, x, y, z. So a 4:1 mux would be an appropriate use. Let us try to write the truth table corresponding to this logic expression. There are 4 high states. Try to compare the patterns with any one of these variables. The first 2 patterns, f is exactly equal to z. For the second 2 patterns, it is complement of z. Z is nothing but one of the variable. F is 0, F is 1. So here the 4 data inputs are correspondingly connected to z complement z, 0 and 1. We are able to get the function f, which is equal to the given logical expression. Similarly here, using 4 variables, function f can be realized using 8:1 mux. So A, B, C are the 3 select lines. The 4th one D, the 4th one D. So now the output f, you are trying to express it in terms of the variable or zeros and ones. For the first 2 combinations, f is D. Second also, you can see it is f is just equal to D. But here it is getting complementing, so it is complement of D. It is 0, 0. Here it is D, 1 and 1. So the proper lines, 0, 1, 2, all the proper input lines by connecting to D or either 0, 1, f can be the logical expression given, as given. Take it as an exercise to realize the full adder using suitable multiplexer, and also realize half subtractor using a mux. Also try to realize the expression function f using mux. To present this, I have referred the following sites. Thank you.